So this is assignment DC electricity. We have already from 1 to question 16 session is recorded. So we'll start with question 17 and onward. In question 17, a copper wire which is having a radius of 0.4 millimeter and it carries a current of 5.1 ampere. So we have the current and we have radius, but that is in millimeters, so we should have in meter. So we divide by 1000 or it will be 0.4 into 10 to the power minus 3 meters. We have to calculate a drift velocity of electrons in the wire. The number of charge carrier for a copper, the value of n is 8.5 exponent 28. So we have the formula, the transport equation, I, the current is equals to N A Q V, where I is a current, that is 5.1. And the number of charge carriers per unit volume, which is 8.5 into 10 to the power 28. Area of the cross section of the wire, which is pi r square. So area of cross section of wire is pi r square. So pi will be 3.14 and r, that is the radius of this, which is 0.4 into 10 to the power minus 3 and then square. Q is a charge of one electron, which is 1.6 into 10 to the power minus 19 coulomb, and V is the drift speed, which we are finding. So when we simplify, like this whole factor is multiplied, the other side it will be divided. So when we divide, it will come out as 7.5 into 10 to the power minus 4 meter per second. That is the drift speed or value of V. In question 18, a student investigated how the light intensity affects the resistance of light-dependent resistor or LDR. She set up the circuit using a cell with a negligible internal resistance. So there is no voltage loss internally as we consider that the cell is having a negligible internal resistance. So she set up, as you can see, the EMF of the cell is 1.5. So EMF of the cell is 1.5. When the light in the lab was switched off, so when the light is switched off, when there is no light or a very small amount of light, like low light intensity, what happened to resistance of LDR? It will increase. If the resistance of LDR will increase, there will be more voltage across LDR. Comparative voltage will be higher, like depending on the resistance of the two, but the voltage across LDR will increase when it gets dark. But again, the division of the voltage between the fixed resistor and the LDR depends on their resistance. Maybe even if it's dark, resistance of LDR increase, but that resistance of LDR might be smaller than the resistance of a fixed resistor. So total voltage here across LDR will be smaller as compared to the fixed resistor. So when the light in the lab were switched off, the voltmeter read 1.19. So reading on the voltmeter is 1.919 volts. Calculate the resistance of LDR when the lights were off. So we want the resistance of LDR. Now, we know they are in series, like this is a potential divider circuit, so total voltage will divide between them. So if the EMF is 1.5 and out of 1.5, 1.19 is here, so remaining from 1.5, 1.19 is volts across the fixed resistor, so remaining voltage will be there across the LDR, which will be 0.31 volts. And what about the current? Because they're in series, so what current passes through the fixed resistor? Same amount of current will pass through the LDR. So how to know the current here? V is equals to IR. So I is equals to V divided by R. V is the voltage across the fixed resistor. And R is the resistance. It's written 5 kilo ohm, which is 5000 ohms, or we can also say 5 into 10 power minus 3. So when we divide this, we'll get the current here, which is 2.38 into 10 power minus 4 ampere. So this 2.38 into 10 power minus 4 will pass through the fixed resistor. Same amount of current will pass through the LDR because they are in series. So when two components are in series, they will have the same current. So the current will be 2.38 into 10 power minus 4. Now we need the resistance. So we have the current in the LDR and we have the voltage. So V is equals to IR. So R is equals to V divided by I. Where resistance, we want the voltage a current ratio. Voltage is how much? 0.31 and current is 2.38. So 2.38 into 10 power minus 4. So when we divide, we get the resistance, which is about 1300 ohms. So this is about the resistance of the LDR, light dependent resistance, at when it is dark. The next part, when the lights were switched back on, the student discovered that it was impossible to calculate the resistance of LDR using this circuit. Like we cannot calculate the resistance of LDR. The teacher said that with the lights on, the resistance of LDR is about 9 ohm. Explain why the student was unable to use the circuit to determine the resistance of LDR with the lights on. The resolution of a voltmeter is 0.01. Like this is the smallest value which a voltmeter can record, that is 0.01. So what we will do, first we'll find what will the voltage across the fixed resistor if the lights are on. So we can use a voltage because when the lights are switched on, the resistance of LDR is 9 ohm. This component is having a resistance of 9. And the total voltage is still 1.5. And the EMF, the total, that is 1.5. So if I need the voltage here, we can use a potential divider formula. Voltage across the fixed resistor is V1, voltage across LDR is V2. So what we can say, V2, the voltage across the fixed resistor is resistance of that part, which is 5000 or 5 exponent 3, divided by the sum of the resistance, 5000 plus 9, and into combined voltage, that is 1.5. So 5000 divided by 5009 into 1.5. If you're finding the voltage, yes, this is V1, not V2, because I said voltage across the, I said the voltage across the fixed resistor is V1, so this is V1. So what voltage we'll get? We'll get about 1.497 volts. So this is 1.497. So how much the reading has changed if you compare, like the maximum reading on the voltmeter, because the maximum voltage can be 1.5, and when the LDR is having a resistance of 9, the minimum voltage will be 1.497. So how much is the difference of the two values? The difference of the two values will be 0.003. So this change in the voltage can be the maximum change in the voltage can be 0.003. But the voltmeter accuracy is only 0. As I mentioned here in the question, that voltmeter is only accurate to 0.01. So can this voltmeter record this small change? Voltmeter can record a change of 0.01 volts. But because the change in the reading, the maximum reading can be 1.5 across a voltmeter, and the minimum reading is 1.497. So this change cannot be recorded. Why this change cannot be recorded? That because that is smaller than the accuracy or the least count of this voltmeter. That's why this voltmeter is not accurate, or this circuit is not accurate to measure the voltage, measure the resistance of LDR. Like the voltmeter will not record this change. It will show the same reading, even the lights are switched on. So as the resistance of the LDR will decrease, the voltmeter reading will increase. So potential across the LDR become like less than 0.01. Like the change is less than 0. So it won't be able to record that voltage. Then we have another question. As you can see, the graph shows how the current vary with the potential across a filament. And for negative temperature coefficient thermistor means negative temperature coefficient refers to a component in which if you increase the temperature, resistance decreases. But for others, like which are following the Ohm's law, are also known as the ohmic resistor. So when current on y-axis and voltage on x-axis, what's the slope represent? Slope represent reciprocal of the resistance, because resistance is voltage divided by current. But here it's current divided by voltage, so it will be reciprocal. What happens? Slope is decreasing, so resistance will increase. But for other one, again the slope represents reciprocal of resistance, so slope is increasing. So what happened to resistance? The resistance will decrease. So for thermistor, the resistance is decreasing, but for filament bulb, the resistance is increasing. We have to explain the shape of each graph and see the weightage. It's of 6 marks. Your answer should include reference to the movement of conduction electron in each component. Like how the electrons will move in each component, you should include that as well in your answer. So first, for a filament bulb, what is happening? The resistance is increasing as the potential difference increases. And what is the reason for that? This will increase the number of collision between the, because what will happen, like more electrons will collide with the lattice of positive ion. So this will increase the temperature. And as the temperature increase, the particle will move faster. So there will be increased rate of collision between the electrons and ions or atoms, which leads to a high resistance. So the points which you will mention here, the first one, what is happening? Resistance is increasing as the potential increase. That is the one point for a filament. Then what will happen? This leads to increase in temperature, which increase the vibration of ions in the lattice. As a result, there will be more collisions between electrons and ions, leads to increase in resistance. This is the case for the fixed resist, this one, filament. The second one is thermistor. But what happened for thermistor? As you can see, the resistance decreases as the potential increases. Like we are increasing the voltage, but the resistance is decreasing. And what is the reason for that? that as the temperature increase, there will be more charge carrier or conduction electron increases. So resistance decrease as the potential difference increase for thermistor. That is one thing. What we about the second point? The second point will mention the temperature increase because current is also having a heating effect. So temperature always increases when there's a current through any device or a component. So temperature increase, which increase the number of charge carriers, like more electron and hole pairs are generated, or number of the charge carriers will increase. As a result, what will happen? So more charges which reduce the resistance. Like greater number of charges or more charges are there, as a result, the resistance will decrease or reduce. So this is the comparison between the filament and the thermistor. Is it clear, this one? The two graphs, like how we explain here what happened, because the slope is representing reciprocal of the resistance. Other one also slope is reciprocal of the resistance. So what happened when we increase the voltage? As you can see, the slope is decreasing, so resistance increase. Here, when we increase the voltage, slope is increasing, it means the resistance decreases. If the slope decrease, resistance increase, slope increase, resistance decrease. That's the first point. The second point, why? Because in a filament, which is a metal, tungsten, so they have different structure. A metal consists of a lattice of positive ion and the delocalized electron. So as the temperature increases, there will be more vibration of the lattice, like these particles will vibrate faster. They will not allow the electrons to move through the structure. Where in case of the semiconductor, which is having like silicon or germanium as a main base element, so when the temperature increase, like we are increasing the voltage, so temperature is also increasing as a result of heat energy. These electrons will come out from the structure, so number of the charge carrier increases. But in case of metal, the number of the charge carrier does not change, it is constant. Drift speed, always remember, when the temperature increases, the drift speed will also decrease. Here also, drift speed will decrease. But increase in the charge carrier is more than decrease in the drift speed. That's why the current will be high, or we can also say the resistance will decrease. In this question, a student carried out an experiment to determine the resistivity of a nichrome wire, alloy of nickel and chromium. Her circuit includes an ammeter, a voltmeter, and a variable resistor. Complete the circuit diagram. So this is a nichrome wire. So we have to complete a circuit diagram. We will measure the voltage, because if you want, so we'll measure the voltage here by using a voltmeter. We'll measure a current by using an ammeter, always in series. Then we have a variable resistor, a battery is there, a switch. And how we use this circuit to determine the resistivity. So we have the formula R. Resistance is equals to resistivity L length divided by A. So if I need resistivity, it will be RA divided by L. So how to get R? How to get the resistance? Resistance will be the ratio between voltage and current. Or what I can do, I can like plot a graph between voltage and current, like different values of voltage and current. In the slope, if I plot a graph for voltage on y-axis and current on x-axis, slope represent R. So I'll get value of R. How to get A? Area of cross section of wire. So I will use a micrometer. I will determine the diameter, and using a diameter, I can find radius, and radius, using that radius, area of the cross section of wire, pi r square. Or if I'm using a diameter, then I can use pi d square by 4. Same thing. Then how to measure the length? You can use a meter scale or a ruler and avoid a parallax error and measure the length directly. So we'll have length, area, resistance. We just substitute to get resistivity. The student varied the length of a nichrome wire in the circuit. For each length, she measured the potential across a nichrome wire. She used a variable resistor to keep the current in the wire at 0.2 ampere. During the experiment, the student plotted a potential difference against the length graph of a nichrome wire. So, student plotted a graph between voltage and length, like changing the length of nichrome wire used. She is measuring a voltage plot. Determine the resistivity of a nichrome. The cross-section area is given. So how we can determine the resistivity? If we have the formula R equals rho L divided by A. If I need resistivity, it will be RA divided by L. So rho is equals to RA divided by L. What about resistance? Resistance is actually a ratio between voltage and current. So in place of resistance, I can write voltage divided by current. So V divided by I, then it will be A and L. Now, student kept the current same. As you can see, the current in dimension, she kept at 0.2 ampere. So the current does not change. That remains 0.2. So I can also write like V divided by L is equals to A in V divided by L equals to AI. Like V into L, V into A divided by L into I. How to get V divided by L? Basically, it's a ratio of voltage and length. Area is there, current is there, so V divided by L. So student plotted a graph between voltage and length. So as the student plot a graph between voltage and length, so if I find the slope here, because remember the gradient of the graph is a quantity on y-axis divided by quantity on x-axis. So on y-axis I have potential, on x-axis I have length. So when I divide them, I will get the ratio. So if I find the gradient of this straight line by using a formula y2 minus y1 over x2 minus x1, the gradient itself, because gradient is a slope and slope itself is a ratio between the quantity on y-axis divided by quantity on x-axis. So that is V over L. So resistivity is equals to V over L into area divided by current. So V over L, how I'll get V over L? I'll get the slope of this graph. How I'll get area? That is given and current is given. So I just multiply. We'll get the resistivity of this wire. The next part, calculate the power dissipated from a nichrome wire to the surrounding when the length is 0.75 meter. So power dissipated means how much power is lost when the length is equals to 0.75 meter. So we have different formulas of power. P is equals to I square R. P is equals to V square over R. So first we'll use like P is equals to VI. We can use the current does not change. When we want how much power dissipated when 0.75 meter. So using the graph 0.75 meter. So each box is represent 10 boxes are equal to 0.2. So each box is 0.02. So 0.72, 0.74, 0.76. So in between them will be 0.75. So we'll draw a line and work out the voltage. So each box, 10 boxes equals to 1. So each box is 0.1. So this is 3.1. volts. So we have the voltage 3.1 and we need the power. So P is equals to VI. So 3.1 multiplied by 0.2 because we maintain the current in each case it's 0.2. So when we multiply them, we'll get a power as 0.62 volts. That's the power dissipated. So using the length, we work out how much voltage and voltage multiplied by current will get the power. In question 21, a source of EMF with no internal resistance is connected in series across a negative temperature coefficient thermistor. Means if we increase the temperature, the resistance of thermistor will decrease. The current and the current in the thermistor and the potential across thermistor are measured. The temperature of the thermistor increase. Which of the following will be observed? So what we will see or what we'll observe if we plot a graph as we did previously, there was a question in which we were having a thermistor, negative temperature coefficient thermistor. So when the temperature was increasing, the resistance of a thermistor was decreasing. This was the shape of the graph, whereas in this case, the slope is reciprocal of the resistance. So if the slope is increasing, it means the resistance was decreasing. So when we check the options, decrease in current, that is not the right way. Why decrease in current is not correct? Because what will happen, resistance of a thermistor is decreasing and resistance is the ratio between voltage and current. Decrease in potential, the potential we are changing, like it's a independent variable we are controlling, we are applying. Like example, if I apply 10 volts, 20 volts, 30 volts, so because we this is the only component, as you can see, read the question, like a thermistor is there which is connected with a battery. So example, there's a battery with no internal resistance and we have a thermistor, and if you connect a voltmeter here and an ammeter, so the reading of the voltmeter does not depend on the condition of thermistor because this is the only component. What voltage I apply, same voltage I will receive on the thermistor. Like if I apply 2 volts, there will be 2 volts across thermistor. If I apply 3 volts, there will be 3 volts. So it does not make any difference. The change in the potential cannot be an answer, like increase or decrease cannot be an answer because that is we are changing. If we change the battery, the potential will change. If we increase the voltage, the potential will increase. If we decrease the voltage or EMF, the potential will decrease as well. But what will happen? Because as the resistance is decreasing, so current will increase. So that's why C is the right answer. Is it clear? Question 21. Which of the following equation does not include any SI base quantity? So SI base quantity, we have length, time, temperature. So this one is SI base quantity that is included. This one is SI base quantity that is included. Current is also SI base quantity that's included. But in D, you can see like there is no SI base quantity included. W is the work done, Q is the charge, and V is the voltage. So D is the right answer. In question 23, a potential difference applied across a sample of a metal wire. So there is a current in the wire. The charge carrier have the drift speed V. Without changing a potential, a second identical wire is placed in parallel to the first one. What is the drift velocity? Like what we did, there was a fixed resistor, like it's like a metal wire is there, or you can say a fixed resistor, in which the drift speed is V. Now what we did, we take identical wire, we did not change anything, and we connected this identical wire in parallel. So another identical wire is connected in parallel. The question is, what happened to the drift speed? So look, the formula, the transport equation, that is I is equals to N A Q B. Now, when we connect, like example, here the total current, when it was a single resistor connected to the same battery. So example, if this is a 2-volt battery, here also 2 volts. So here potential 2, here also potential 2. They have the same area. Area does not change. This is constant, Q is constant, and N is the number of charge carrier, that is also constant for metal. So what happened to the current here? Because the total current in the circuit will be double. No, the here also V is there. Total current in the circuit will be double. Like example, if here the current is say 2 ampere, here the current will be 4 ampere. But that 4 ampere will divide as 2 ampere and 2 ampere. And then again it recombined to 4 ampere. Because when they are connected in parallel, the combined resistance of a circuit will decrease, so the total current in the circuit increase. But we want to find across each of them, as the charge carrier in the wire, uh, the drift speed is there without changing the potential, a second is placed in parallel. So what is the drift velocity? What will happen to drift velocity? It won't change at all. Because drift velocity depends on how much voltage we apply, what is the resistance, what is the length, many factors it depends on. So in this case, what happened? Because the conditions are same 2 volts is applied, that's why the drift velocity does not change. But what if this same question was there and they say we connect them in series? So now what will happen? Because when we connect two components in series, so the resistance, when we compare here, resistance will be R1 plus R2. Means the combined resistance will be high. If the combined resistance increases, so the current will decrease. If the current decrease, I is equals to N A Q V. So N is not changing, A is not changing, Q is not changing. So what happened to V? V will decrease. So in that case, V will become half. But in this one, like this will be V by 2, this also be V by 2. But because here it connected in parallel, so when they're connected in parallel, it receives the same voltage. That's why the drift velocity will also be same. A student investigates a relation between a current and potential difference. Uh, Here, one is a potential divider circuit, another one is a variable resistor circuit. State one advantage of using a potential divider circuit. Like this, a potential divider circuit, this one is a variable resistor circuit. So, what is the advantage? In a potential divider circuit, the voltage can be reduced to zero, like across the component, because two circuits look identical, but one is we are using all the three ends, another one we are not using all of them. Here, what happened? If I move this part, the movable part, the sliding contact, if the sliding contact is here, so if the sliding contact is here, this part will have zero voltage, and all the voltage, like example, if the 10 volts apply, all the 10 volts will be across this one. So across the component, we can divide the voltage, or voltage can be zero. But here it can be. Like if I move the potential across the component cannot be zero in a variable resistor circuit. Like if I connect here, So if it's a 10 volt supply, the charges have to pass through this component only, so all maximum 10 volts will be there. But if I move this sliding contact, if I move the sliding contact here, now like this resistor and component are in series, so voltage will divide. So if it's a 10 volt, maybe like if they have the same resistance, 5 volts here, and remaining, like because it charges, so remaining 5 volt will be across the component. So we cannot achieve 0 volts across the component in a variable resistor circuit. But in a potential divider circuit, the voltage can be reduced to 0. That's the advantage of potential divider circuit over a variable resistor circuit. Then we have the resistance R is there. We have a diameter, resistivity is there, and length is there. So we'll use a formula R is equals to rho L divided by A. So first we'll find the area of cross section, and after getting the area, we'll use a formula pi r square. We'll get the radius, and after getting the radius is half of diameter, so radius multiplied by 2 will get the diameter. So using the first formula, we get area. Using area, we get radius. And using radius, we get the diameter. So direct substitution are there. And don't forget to convert length into meter. Another potential divider of length 40 centimeter, resistance 50 ohm, has a potential of 12 volt upright. The potential is measured across 7.16 centimeter while calculate this potential.